All right, hello everyone, and welcome to my channel. This channel is for educational purposes, and we take a look at some great theories of everything from the past, ancient and modern, and show how they work, and try to help you employ them in your own life in order to help you with your paradigm shift or awaken to 5D consciousness, to fill out your holistic worldview, and any other benefits that you might be able to glean from these. Today is our 496th video that we've done on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson worked as an engineer in the US in the 20th century. He died in 1990, and for the 60 years prior to that, he was working out his reciprocal system. In 1959, he articulated his two fundamental postulates after many, many years of research and inductive reasoning. He boiled it all down to two sentences about how he believed the universe operated, and in doing so became one of the pioneers to attempt to build a universe of motion, not a universe of matter, not a universe of energy, but a universe of motion. And Larson's postulates read, the first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then Larson's second postulate is basically what he uses to derive his theoretical universe. He takes his first postulate and kind of plugs it into the second postulate. And so, in my mind, the first postulate is almost infinitely more important than the second postulate. But the second postulate reads, the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So Larson takes his ideas about this universe of motion, and he plugs them into a universe that is, operates on the basis of math and geometry and logic, and it spits out Larson's theoretical universe. What the universe would look like if Larson's postulates were correct. And then in a lot of his subsequent research, Larson compares his theoretical universe with the empirical universe of legacy science, what the army of scientists had come up with in terms of all their laboratory experiments and scientific tables in particular. So in this book here that we're looking at, that we will be looking at today, and that we have been looking at for a while, is called Basic Properties of Matter. So this book is on chemistry, and it talks about many of the basic properties of matter, such as electric charge, the melting point, the compressibility, the specific heat, these kind of properties that are possessed by all kinds of matter, atoms, compounds, and they all, have been tested in the laboratory. What is the melting point of, silicon? And They come up with a value from the laboratory. Larson comes up with an equation for the melting point of silicon, and then compares his results that come strictly from theory, no testing, no laboratory, no army of scientists to do a battery of tests and have billion-dollar grants in order to conduct such things. And Larson, in many cases, is really able to reproduce the scientific tables strictly from theory. Within 1% or even sometimes 0.1% of the actual values or the laboratory tested values. In many cases, Larson is correcting them because in some cases, like with compressibility, the laboratory scientists are not able to really make terribly accurate predictions or measurements. And so they admit that they're, okay, well, we can't really measure this more than within 10 or 20% of the actual value. But Larson's theoretical values cut right through that. And so in many cases, Larson's values are, more trustworthy than the legacy scientists that have taken up millions, if not billions, if not trillions of dollars of our taxpayer money. And, over the course of centuries, with thousands, and if not hundreds of thousands of scientists all lined up to participate in this. And this one dude with no resources and no help is able to reproduce what they can do. So you think he's probably onto something. Okay, now if you want to go deeper into Larson's theory, into the fundamental postulates and what the ramifications are, what they really mean, what does it really mean to be a universe of motion, and where do these three dimensions and these discrete units and the two reciprocal aspects, space and time, all fit in? You want to watch any of my first 474 videos on this subject. I kind of go into these matters at least, for 20 minutes or so to kind of give you at least the once over so that you are, a little bit up to speed when we get into the reading. Now today in this video, I'm pretty much going to assume that you're kind of up to speed enough to at least have some of the basic questions answered. And we're going to read right from chapter 15, which is on electrical storage. And we've been reading this chapter a few days, so we are hopefully going to finish it today, or at least get close to the end. Now, in this chapter, Larson is having trouble because, in Larson's system, everything is made out of motion, and motion is made out of space and time. And so all of our fundamental quantities are relationships of space and time and can be described exclusively in space-time terms. And so that's where he derives his units from. For example, speed. Speed is a kind of motion. Speed is, the car is moving 15 miles an hour. 15 miles of space in 1 hour of time. That is space over time. Space over time is speed. And all of our other scientific quantities are also fractions, with space or time as the numerator and time or space as the denominator, such as matter. Matter is time to the third power over space to the third power. Energy is time over space. Acceleration is space over time to the second power. Force is time over space to the second power, and so on. Now, in this chapter, Larson identifies electrical capacitance The MKS unit for that is the farad. And he identifies the farad as S, which is also the unit of electrical of the electron. The electron is a unit of space. In Larson's system, the electron is uncharged. It can take a charge, but in its natural state, it is uncharged, and it is a rotating unit of space. Just like everything else in Larson's system, it is a kind of motion. The electron is a rotating unit of space. It can take a charge. A charged electron is a rotating unit of space, but a charge is a rotational vibration. Rotational vibration would look like that. And so that is what a charge is. Most scientists believe that an electric charge is simply an electron. You know, give an electron to matter and it becomes charged. But in Larson's system, it is give the motion that is a rotational vibration to matter and it becomes charged, including the electron. You can also put a charge on an electron. But in its natural state, an electron or electric current is simply space. Electric current is space over time. The speed, whereas the electric charge is a unit of energy, time over space. And so in Larson's system, he derives that electrical capacitance is simply S. But some of Larson's associates disagreed with that attribution. And this guy, Dave, proposed that capacitance is actually S to the third over T. And Larson has spent the last several pages trying to justify his S. And I don't know that he was actually aware of the possibility of using S to the third over T. But if he had done that, the S to the third over T seems to satisfy every equation perfectly, whereas in Larson's system, the S, it works some of the time, but some of the time it doesn't work, and Larson ends up kind of trying to wiggle out of it by claiming that there are two forms of the Coulomb, which is supposed to be the unit of electric charge, capital Q. But Larson has to come up with a capital Q and a lowercase q. And he plugs in lowercase q into several of the classical equations in order to balance them out, space-time wise. And he does it to his own satisfaction, but it definitely does not satisfy me. And I'm not saying that he's right, he's wrong for sure, but that's the question I have. So that's what we're moving forward with. I think he just identified permittivity, and that we're going to go forward looking at permittivity, which is kind of like the resistance to forming an electric field. Again, we have to keep in mind the fundamental distinction between the electron and the electric charge. Those are two different things. One of them is units S, the electron, and one of them is units T over S. One of them is involved in electric current, S over T, and the other one is static electricity. Okay. Permittivity is of importance mainly in connection with non-conducting substances or dielectrics. If such a substance is inserted between the plates of a capacitor, the capacitance is increased. The rotational motion of all non-conductors contain motion with space displacement. It is the presence of these space components that blocks the translational motion of the uncharged electrons through the time components of the atomic structure and makes the dielectric substance a non-conductor. Nevertheless, dielectrics, like all other ordinary matter, are predominantly time structures. That is, their net total displacement is in time. This time adds to the time of the reference system and thus increases the capacitance. From this explanation of the origin of the increase, it is evident that the magnitude of the increment will vary by reason of differences in the physical nature of the dielectrics, inasmuch as different substances contain different amounts of speed displacement in time, arranged in different geometrical patterns. The ratio of the capacitance with a given dielectric substance between the plates to the capacitance in a vacuum is the relative permittivity, or dielectric constant, of the substance. The dielectric constants of most of the common dielectric substances, class A dielectrics as they are called, show little variation at low frequencies under ordinary conditions. This indicates that permittivity is an inherent property of the substance, a consequence of its composition and structure, rather than of its relation to the environment. This is consistent with the theoretical explanation given above. Conventional theories of dielectric phenomena are based on the premise that these phenomena are electrostatic in nature. It should be understood, however, that all theories which depend on the existence of electric charges in electrically neutral materials cannot be other than hypothetical. Furthermore, conventional science has no comprehensive electrostatic theory of dielectrics. As expressed by W.J. Duffin, quote, "It is important to realize that calculations of fields due to and forces on charge distribution are performed on a model and the results compared with experiment." And then he goes on, "Different models are required to account for different sets of experimental results. In the model that is applied to the capacitance problem, it is assumed that positive asterisk and negative asterisk charges exist in the electrically neutral dielectric." And Larson, if you haven't been listening, Larson uses this asterisk to indicate that he's using the conventional terminology. In Larson's system, the negative charge is actually positive, and the positive charge is actually negative. But those go against the conventional nomenclature. So he uses the asterisk to indicate that he's using the conventional nomenclature. Okay, so positive asterisk and negative asterisk charges exist in the electrically neutral dielectric. That, quote, "small movements of the charges have taken place in opposite directions," end quote. And 3, that these movements produce the polarization which we believe takes place, end quote. As this statement by Duffin concedes, there is no direct evidence of the polarization that plays the principal role in the theory. The entire model is hypothetical. Clarification of the dimensions of the quantity known as permittivity eliminates the static charges from the mathematics of the electrical storage process, and thereby cuts the ground out from under all of the electrostatic models. The customary mathematical treatment is carried out in terms of four quantities: the displacement, D, the polarization, P, the electric field intensity, E, and the permittivity, which is abbreviated with some letter that I'm not familiar with, but it looks kind of like an E, written a little bit in half lowercase and half uppercase, but it's basically EO. These quantities, the investigators tell us, are related by the expression P equals D EO E. We have already seen earlier in this chapter that the space-time dimensions of D are 1 over S, and those of permittivity, EO, are S squared over T. The dimensions of the quantity EOE are then S squared over T times T over S to the third, which he didn't tell you that has already been determined in this chapter, electric field intensity. And that comes out to be 1 over S. It follows that the dimensions of P, polarization, are also 1 over S, just like displacement, D. We thus find that all of the quantities entering into the dielectric processes are quantities related to the electric current, the electric quantity, S, the capacitance, S, in Larson's system, S, in Dave's system, and the RS2 system in general, S to the third over T. The displacement, 1 over S, the polarization, 1 over S, and the quantity EOE, which likewise has the dimensions 1 over S. No quantity with the dimensions of charge, T over S, has any place in the mathematical treatment. So it does sound like that is a step in the right direction, because in Larson's system, all of this that has to do with capacitance is uncharged electrons. And so there should be no place for the charge T over S in any of these equations. Now that this seems to be, this is far more palatable to me than what he came up with just a few pages ago when dealing with capacitance in general, although he's still making this other attribution. One of the complications that occurs is that, for example, with permittivity and also magnetic permeability, the value for it is often very close to 1. And so it doesn't show up in equations because it seems like it's almost invisible. And I believe in Larson's treatment here, it doesn't have any units, dimensionless. So it's kind of like a phantom. Continuing on. The language is that of electrostatics, using terms such as polarization, displacement, etc. And an attempt has been made to introduce electrostatic quantities by way of the electric field intensity, E. But it has been necessary to couple E with the permittivity, EO, and to use it in the form of EOE, which, as just pointed out, cancels the electrostatic dimension of E. Electric charges thus play, because that's what permittivity does. Permittivity is the resistance to forming an electric field. Electric charges thus play no part in the mathematical treatment. But I'm not totally convinced of that, because is the electric field charged? Okay. A similar attempt, as you can tell, I'm not any type of expert on this. I'm a historian, and so I'm doing the best I can here, trying to present a topic that I think is vitally important, not really so much just for the purposes of understanding electricity and magnetism. Larson's reciprocal system is a theory of everything. So what he finds in one field is analogous to what he's going to find in another field. And so I feel like it is important to look at his works in several different subjects: electricity, magnetism, chemistry. We've already looked at his stuff, a lot of stuff on atomic physics, some stuff on astronomy, metaphysics, religion, economics we're going to be looking at. And so you need to be, in my opinion, to get a broad, well-rounded approach of all the different things that the reciprocal system can do, or at least the ones that Larson looked at, because it can be plugged into any theory. So what you're really trying to do is look at the analogies, look at the connections, look at the methodology, so that you can, once you learn the theory, that you can apply it to whatever subject you would like to apply it to. Okay, back to Larson. A similar attempt has been made to bring the electric field intensity, E, into relations that involve the current density. Here again, the electrostatic quantity, E, capital E, is out of place and has to be removed mathematically by coupling it with a quantity that converts it into something that has a meaning in electric current phenomena. The quantity that is utilized for this purpose is conductivity, symbol omega. No, I don't know my Greek letters very well. Maybe that's rho. Either way, it's some Greek symbol. Space-time dimensions s to the second over t to the second. The combination conductivity times electric field intensity has the dimensions, s squared over t squared times t over s to the third equals 1 over st. These are the dimensions of current density. Like the expression EOE previously discussed, the expression of the electric field intensity times the conductivity has a physical meaning only as a whole. Thus, it is indistinguishable from current density. The conventional model brings the field intensity into the theoretical picture, but here, again, it is necessary to remove it by a mathematical device before the theory can be applied in practice. In those cases where the electric field intensity has been used in dealing with electric current phenomena, without introducing an offsetting quantity such as conductivity or permittivity, the development of theory leads to wrong answers. For example, in their discussion of the theoretical basis of Ohm's law, Blaney and Blaney say that, quote, when an electric field strength E acts on a free particle of charge, Q, lowercase q, the particle is accelerated under the action of force, end quote. And this, quote, leads to a current increasing at the rate of di current over dt equals n times the quantity lowercase q squared over m. the quantity times E, end quote, where n is the number of particles per unit of volume. The space-time dimensions of this equation are 1 over st times 1 over t equals 1 over s to the third times s squared times s to the third over t to the third times t over s to the third. Thus, the equation is dimensionally balanced, but it is physically wrong. As the authors admit, the equation is, quote, clearly at variance with the experimental observation. Their conclusion is that there must be, quote, other forces which prevent the current from increasing indefinitely. This fact, that the key element of the orthodox theory of electric current, the hypothesis as to the origin of the motion of the electrons, is clearly at variance with the observed facts, is a devastating blow to the theory, and not all of its supporters are content to simply ignore the contradiction. Some attempt to find a way out of the dilemma and produce explanations such as the following. When a constant electric field E is applied, each electron is accelerated during its free path by a force of minus lowercase e, which I don't know what that is. But at each collision, it loses its extra energy. The motion of the electrons through the wire is thus a diffusion process, and we can associate a mean drift velocity v with this motion, end quote. But collisions do not transform accelerated motion into steady flow. If they are elastic, as the collisions of the electrons presumably are, the acceleration in the direction of the voltage gradient is simply transferred to other electrons. If the force EQ, lowercase q, actually existed, as present-day electrical theory it contends, it would result in accelerating the average electron. The authors quoted in reference 54 evidently recognize this point, but they fall back on the prevailing confidence that something will intervene to save the moving charge theory of the electric current from its multiplicity of problems. There must be other forces that take care of the discrepancy. No one wants to face the fact that a